Right, hi, Mr. Dillo today, and today we're going to do some at-home science. So welcome to the virtual lab, where safety is the #1 priority. So today, let's say that you have invented a brand new snack, and this snack is so good, it's so tasty, it's so amazing, it's going to put Hot Cheetos out of business. But you've got to put the little label on the bag. You have to say how many calories are in your snack. How would you figure that out? Well, you can figure that out using the energy equation and actually computing how much energy is in your new snack. So the energy equation goes a little something like this. Q equals MC times delta T. And that is to say that the energy contained in a system, your snack or any other system, is equal to the mass of that snack times the specific heat of the snack times the temperature change. Ran out of room there. Temperature change. Okay, so we can use this equation to determine the energy in your food. How would you do that? Well, for example, let's take marshmallows. Now, you know that if you've ever been near a campfire and you've made s'mores before, that you can combust marshmallows and you can release that energy. So it turns out that combustion is not too much different from what your body does with the individual little molecules, the sugar molecules that are in this marshmallow. Your body is going to use chemical reactions to release the energy of this marshmallow, just like when you burn it and it catches on fire on a campfire. So why does that happen? Well, some molecules, when they rearrange to form new molecules in a chemical reaction, release energy, and we call that an endothermic or exothermic reaction. What do you think? It would be an exothermic reaction because the heat energy goes out. So what we can actually do is we can combust this marshmallow, completely release all of the energy that's in this marshmallow, and measure how much energy change there is based on this equation. Now, if we just combusted it, it might be difficult to catch all of that heat and temperature change of the air. So how can we fix that situation? How can we transfer all of the energy of a marshmallow to something where we can actually measure the temperature change? Well, why don't we use water and heat up the water and see how much the temperature changes in the water, and then we can measure the energy that way. So if you look on the back of a bag of marshmallows, you'll see, and I'll try to get this close so you can see it, that there's nutritional information here. So what we can see is that there are 4 pieces per serving, and amount of calories per serving is 100. And if just notice that that's an uppercase C. So uppercase calorie is a little misleading, because an uppercase C calorie is actually 1,000 lowercase c calories. So 1 calorie that you see on a package of food like Hot Cheetos or marshmallows is going to equal 1,000 little c calories. So we also call this uppercase C calorie. It's actually called a kilocalorie. So it's a little misleading there. But this kind of calorie is what you can use to plug into this equation. And it's generally what is used in science. Also, the joule is used for energy. But anyways, there's 100 calories in 4 marshmallows. So 1 marshmallow is going to have 25 calories. But if it has 25 big C calories, that means it has 2,500 100 little c calories. So what we will do is we will actually combust the marshmallow, and we will see all of the energy change that we get using this equation, and then we'll compare it to what the label actually says and see how close we actually get. So the first thing that we need to do is measure temperature of our water. So if we're talking about a temperature change, that's going to be from initial to final. It's going to be, right? So TF minus TI. So the initial temperature, which I'm just using a candy thermometer here to measure, looks like about 23? Nah, more like 22. We're gonna go with, this water is 22 degrees right now. So 22. We're starting with the last thing first. Now the next thing that we need to know is what's the mass of our water. So for this, I'm gonna use, it doesn't really matter how much water I use, as long as I know what the mass of the water is. I'm gonna turn on my scale here, make sure it's set to grams, and it is. And then I hit tare the button so that it's at 0. One more time. There we go. And I'm gonna pour some water in here. Let's say about, I don't know. Doesn't really matter what we use. Let's use that. 117 grams of water. So we've got 117 grams of water. 117 grams. Okay. So now we need the specific heat, which is a constant number. It's always the same thing for water. I'll talk about that in a minute. But let's do the experiment first. Now, we're going to heat up water. So what I would like to do is get as much of that marshmallow energy into this water as possible. So what I've done is I've taken a standard Coke can, and metal is a good or poor conductor of electricity. It is a good conductor of electricity, so, but also of heat. So this is going to allow all of the heat to get transferred straight to the water, this container, but I also don't want the heat escaping out. So what I've done is I've wrapped it with some styrofoam. You can't see the styrofoam, but I've wrapped some styrofoam around, and then I've like put this tape around the whole thing to hold it in place. So this is my sort of barrier to keep the heat from escaping, because styrofoam is a good conductor or insulator. So it's going to keep that energy from escaping. So let's just go ahead and put our water in here. You'll notice that I've cut the opening to make it wider, just by a little bit, so that we can get all the water in there easily, but also so that I can stick this thermometer in later. Now I've got the water. How am I going to get the calories from a marshmallow to water? I'm going to have to burn it, and I'm going to use one of these little aluminum cans to burn it in. So I'll just put it right in here. And why do you think I cut this groove out in the front? Well, I cut the groove out so that oxygen can get in, because oxygen is one of the key ingredients for a combustion reaction. But also, hopefully you guys will be able to see a little bit. So I'll set this right here. Again, metal, excellent conductor of heat. And what I'm going to do is turn this little gas burner on. So I hear a little bit of a hiss. Now, before I turn this on, propane is going to come out. I don't really want that energy. So I'm going to turn this on as low as I can possibly can while still combusting the marshmallow. The idea being that I only want the heat from the marshmallow, not from the propane that's coming out of the gas burner. So let's just go ahead and do that. Okay, I hear it hissing. I'm hitting the igniter. Oh, it just ignited. Now I'm going to turn it down a little bit. Okay, and I can't really see the flame, but I saw that the marshmallow just melted a little bit. So that tells me that it's burning. Woo! And now you can see that smoke. So there it goes, it's burning. And oh, this is such a cool lab. I'm really bummed that we don't get to do this at our classroom. I'm telling you guys, this is a great lab. Did this when I was in 6th, 7th grade, and I just thought it was the coolest thing ever. And who doesn't like to burn things? I mean, come on. So what you can see right now is that this thing is really combusting. So I'm going to turn the gas down even more, and I'm just trying to keep as much of this flame directly underneath the my canister as possible. Oh man, it looks like molten lava right now. It's just this mass of black, ooey, gooey, crusty heat. And I could just feel so much energy coming off of this thing right now. Very hot. So what's coming off of this marshmallow right now would be the products of a combustion reaction. So what are the products of a combustion reaction? Woo! It's CO2, which is escaping into the atmosphere, energy, which you can see in the form of light, but also thermal energy, heat energy, that is to say, and water. So you can actually see there's a little bit of condensation that's built up underneath. There's just a little bit of water. Remember, water is one of the products of a combustion reaction. All right, at this point, this marshmallow looks like a black charcoaly mess. So I'm just going to put this in the thermometer. I put the thermometer in here with the water to check the temperature. And just look at that. Get in there. Can you guys see that? It's just like black, charcoaly nothingness. There's no whiteness left whatsoever. All just totally black. Yeah. Another nice thing about marshmallows for this lab, and the reason that we use marshmallows is because they're very simple sugars. High fructose corn syrup, which you might have read something about, it's not particularly great for you. And the reason is exactly for what we just saw. It combusts really easily. So when you eat a bunch of marshmallows or candy, that sugar all goes into your system really quickly. And it gives you that sugar rush, which can be harmful for your system over time because your body sugar levels keep going up and down and up and down. It's like a roller coaster. And eventually what happens over time is that you can get things like diabetes, where your body has the inability to regulate your blood sugar like it should. So if we were to burn a more complex carbohydrate like whole grains, that wouldn't burn as easily, but it would be better for you because it doesn't release all that energy into your system at one time. What they call the sugar bomb effect. Okay, so it's been a couple of minutes. Let's go ahead and check the temperature here. It's right halfway in between 25 and 30, so let's call that 27. 27 degrees. So we went from 27 down to 22. Now, what's the specific heat of water? We would need to know that. So water actually has a constant, and since water is such a important molecule to our lives, the whole system is actually based on the energy contained in water. So it turns out that 1 calorie, and that's the little calorie, 1 calorie, that's the energy it takes to heat 1 gram of water by 1 degree Celsius. So the specific heat of water just turns out to be 1. Okay? So do this equation, see what you come up with. Is it close to this? And then once you're done, how close was I? You can use the percent error calculation, which is on the video that I provided. There's an example, but basically you take your experimental results that you got from the experiment, or from, in this case, what I got from the experiment, and then compare that to the actual, and then times it by 100 to get your percent error. All right, now that we have finished this lab, it's time to do something a little bit different. So what's something else that we can do that's like a little fun with this whole energy thing? Well, what if I wanted to touch a flame? Now, if I just touch this meth propane that's burning right now, it would burn my hand. So like, what's a way that I could have combusting propane in my hand but not actually burn my hand? Well, what has a high specific heat that could insulate my hand? Well, water has a high specific heat. So we have some water here. I've got a bowl of water that some leaf stuff fell in. It's okay. Actually, just pick that out. And we're going to take some dish soap, because what does dish soap do? It produces bubbles. And we can trap the propane inside of those bubbles. So I'm just going to give this a good stir, get it nice and mixed together there. And what I'm going to do is, without actually turning this thing on, I'm just going to open the valve so that the propane comes out. And I'm going to put it in here. And you can see a bunch of bubbles start to form. So I'm just going to let it go like that for a minute. And we're going to get some bubbles that are trapped with propane and butane. And it's all going to build up in there. So methane has one carbon. It's what we call hydrocarbons, because they're made primarily of carbon and hydrogen. And methane is very combustible. It's a gas. Ethane is like natural gas that you get in your home that you cook with. That has 2 carbons surrounded by hydrogens. And then propane has 3 carbons. Butane has 4 carbons surrounded by hydrogen. So what we have is propane and butane here. So what I'm going to do now is I'm just going to get my hands super wet, get that water on, and let's find out if water is a good enough insulator to keep me from burning my hand. What do you guys think? Should I do it? All right, here we go. Woo! Look at that. Hand feels a little warm, but not too bad. Let's try it again. You guys ready? Woo! Woo! I think I didn't get my fingernails very wet. Felt a little hot that time. So how many of you guys would do that at class if I asked you to come up and do a demonstration for everybody? I think we all know about that one person in class that would totally do it. The daredevil. All right, so hope you've enjoyed this. I know it's not as cool as doing it in class, but do your best on the Google form. Email me if you have any questions, and good luck. See you guys next time.